Hello and welcome back. Today we'll practice more techniques for evaluating limits. So, like we covered in the last section, whenever possible, try direct substitution. That's probably the fastest and most effective way to find the limit. With direct substitution, you may get an asymptote. It would be a good idea to graph or use a table to find the limit. The second scenario, which happens a lot when you have a linear function or polynomial, is that you'll get a real number. And most likely than not, it'll be that value. Just be careful if you have piecewise functions or functions that behave differently. And the third scenario is you'll get a function in indeterminate form, so 0 over 0. So if we plugged in -1 here, we'd get 0 over 0. In the last section, we just went back to our failsafe of using a graph or a table to find that limit. Now we're going to look at some ways that we can actually find that limit algebraically. So the first is factoring. So if you can factor, divide, and reduce that expression, you may be able to find the limit. You can also use conjugates. You can multiply the top and the bottom by the conjugate and possibly get the answer. And then finally, with trig identities, you can substitute with different identities for which you can get a value for the limit. When none of these work, you can always use approximation. And that's always going to be the fail-safe, using graphs and tables to approximate limits. Okay, let's go ahead and practice. We would get something in indeterminate form. You could see if we plugged in -3, we would get 0 over 0. So what we could do in this case is factor. So let's rewrite this as the limit as x approaches -3. Factoring the numerator, we get x plus 3, x minus 2, and you can see that x plus 3 will cancel out. And we'll be left with the limit as x approaches -3 of x minus 2. And when we use direct substitution, we get -3 minus 2, which is -5. And you can see from this table, find values that approach -3 from the left, and from the right, they get very, very close to -5. Go ahead and try the next one and come back to check your answer. So we factor the denominator into x squared plus 1 and x minus 1. We can easily see we're going to cancel out the x minus 1's, and we're left with the limit as x approaches 1 of 1 over x squared plus 1. And when we use direct substitution, we just get 1/2. And looking at the graph, you can see that even though there's a hole there, the y value is getting very, very close to 1/2. Now let's look at our second technique of rationalizing and using conjugates. So for the first one, we'll multiply the top and the bottom by the conjugate of the numerator. The square root of x plus 1 plus 1 over the square root of x plus 1 plus 1. We'll get x plus 1 minus 1. And we can simplify that numerator a little bit more, and we'll be left with x on the top, but the x's can reduce. The limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And now let's try direct substitution. So we have 1 over the square root of 0 plus 1, which is just 1. So we have 1 over 2. And you can see from the graph, again, as x approaches 0, we get 1/2. Go ahead and pause the video, try the next one, and come back to check your answer. We can multiply the top and the bottom by the conjugate of the numerator, 1 plus square root of 1 minus x. We can simplify, the x's are going to reduce. We can find that limit with direct substitution and get 1/2. Okay, so remember in the last section we talked about when limits do not exist. And one of those reasons was when a function was approaching a different number from the left and the right. And since that happens so frequently, we can use a notation to show that it is approaching two different numbers. And the way we show it is with one-sided limits. When you see the negative, so as x approaches c from the negative, we're talking about values from the left, or values that are less than c. And then to show that we're approaching from the right, we could say the limit as x approaches c from the positive, or values that are greater than c. So if we're going to find the limit as x approaches 0 for this function, well, we could see the limit will not exist But we can also explain showing this notation. That is, as x approaches 0 from the negative or from the left, the limit is -2. As x approaches 0 from the right, the limit of that function is 2. Showing the one-sided limits explains why the limit does not exist. Another time that we know that limits do not exist when the y value is unbounded, meaning that it keeps going higher to infinity and lower to negative infinity. Again, since that happens so frequently, we can show that with notation of infinite limits. So as x approaches a, the function increases to positive infinity. As x approaches a, then we could say the limit is going to be infinity. And again, we're still saying that the limit does not exist. And we're explaining why, because it's unbounded. The y value is becoming arbitrarily large whenever we take x closer to a. On the other end, if the y value is going down as x approaches a, then we could say the limit is approaching negative infinity. Now let's use those notations to explain why f of x equals 1 over x does not have a limit as x approaches 0. Again, so looking at the graph, as x approaches 0, from the right and the left, the function is approaching different numbers. So as x approaches 0 from the left, f of x is approaching negative infinity. It keeps going down. As x approaches 0 from the right, the function is approaching positive infinity. So let's see if we can put that together in notation. So we're saying as the limit of 1 over x, as x approaches 0 from the left, is going to equal negative infinity. And the limit of 1 over x, as x approaches 0 from the right, or numbers that are greater than 0, that'll equal positive infinity. So again, the limit does not exist in this situation, but we can show with one-sided limits and infinite limits why the limit does not exist. Now let's look at the difference quotient, which we've covered before in chapter 1, but you're going to use frequently next year in calculus. So whenever we find the limit of the difference quotient, we always get an indeterminate form, 0 over 0, as h approaches 0. But we can also use the difference quotient to find the limit of other functions. So if we have the function f of x equals x squared minus 1, and we want to find the limit of this difference quotient, first substitute 3 plus h for x and 3 for x. So f of 3 plus h would just be 3 plus h squared minus 1. That's 9 plus 6h plus h squared. And that just simplifies into h squared plus 6h plus 8. For f of 3, we'll just get 3 squared minus 1, which is 9 minus 1, or 8. Okay, so let's find this limit. So the limit as h approaches 0 of this function, so f of 3 plus h, that was h squared plus 6h plus 8, minus f of 3, which we figured out was 8, over h, that's going to simplify into h squared plus h. So I'm going to factor on h here. And we can easily see that the h's are going to cancel. So we get the limit as h approaches 0 of h plus 6. And we can use direct substitution to find out that limit is 6. There are some other methods that we can use to find limits that weren't on that chart on the first page. The first is the squeeze theorem. The squeeze theorem is saying if you have functions f of x between two functions, h of x and g of x, if the limit of both functions as they approach c equals L, then the limit of f of x as it approaches c must also equal L, because it's sandwiched or squeezed between the two. All right, so let's use the squeeze theorem for a little trick. If we're going to find the limit of sine of x over x as x approaches 0, we would get the indeterminate form of 0 over 0. So we can rewrite it using trig. Another method is to use the squeeze theorem, using the area of a triangle and sector. We know that this is going to be sine of 0. And if we extend the line to the tangent, well, we know that this length here will be tangent of x. So if we're going to find the area of that triangle, it would just be 1/2 times base times height, which is 1 times tangent of x. So that you get tangent of x over 2. If we're going to find the area of this triangle, well, you know that the area again is 1/2 base times height. So 1/2 times 1 times sine x will give us sine of x over 2. And in between those two triangles, we have the area of the sector. And we know the area of a sector is going to be r squared times whatever the central angle is divided by 2. So the radius is 1, so this will be x over 2. If we multiply each of these expressions by 2 over sine of x, we'll get 1 over cosine of x is greater than or equal to x over sine of x is greater than or equal to 1. Now, if we took the reciprocals of these, we get cosine of x is greater than or equal to sine of x over x, which is greater than or equal to 1. Play with these equations a little bit by taking their reciprocals and reversing the inequalities. We get cosine of x is less than or equal to sine of x over x is less than or equal to 1. So we still want to figure out the limit of this function. So what we can do is find the limit as x approaches 0 of cosine of x, and we can find the limit as x approaches 0 of 1. Well, the constant will just equal 1, and remember cosine of 0 is also 1. So since they both equal 1, the limit of sine of x over x as x approaches 0 will also be 1 because of the squeeze theorem. Okay, so the last concept is the idea of limits at infinity. So when we're approaching infinity or negative infinity, functions can also have limits. The limit of f of x as x is approaching positive infinity or becoming sufficiently large, we'll get very, very close to L. And then if we are finding the limit of f of x as x approaches negative infinity, we can also have a limit L. So what that looks like is if we have this function 2x plus 1 over x. So you can see that we're going to have that horizontal asymptote at y equals 2. So the limit as x approaches negative infinity will be equal to 2. And the limit of the function as x approaches positive infinity will also equal 2. Well, that's it for today. We'll go over more questions in class.